All right, let's go ahead and get started. So last time we started on the next sort of second of four chapters of this particular course, talking about randomized algorithms, and we looked at a particularly nice example of a randomized algorithm, which is ultimately just randomized quicksort. We have a bunch of nuts and a bunch of bolts of different sizes, and we need to match them up, but only match it comparing nuts against bolts. And there we were in a situation where doing things quickly with a deterministic algorithm without using randomness is extraordinarily difficult, at least as far as we know. Which is why I talked about it in those terms instead of just talking about sorting, because you could just say, why not do merge sort? What I want to talk about today is a similar problem, and seen in the right light, exactly the same problem, which is I want to talk about balanced binary trees. Search trees in particular. Now, in CS225 and possibly even in other courses, you've seen probably at least one mechanism for keeping a binary search tree balanced. So the design goal for a binary search tree is I want to be able to insert things and delete things and look things up. Possibly doing queries like, what's the largest object in my tree that's smaller than this value? What's the smallest value in the tree that's larger than this given value? So-called successor and predecessor queries. And I'd like to be able to do that, maintain all this information, so that every operation takes me log n time, where n is the current number of objects in the tree. Okay. And there are lots of different ways of reaching this goal deterministically, and I don't remember the details of any of them. Some of you have seen red-black trees, some of you have seen AVL trees, some of you may have seen B trees, which for small values of B you can pretend are balanced binary search trees. There are literally dozens of these things. And especially when it comes to doing insertions and deletions, the precise rules for keeping everything balanced and restoring balance when things go wrong are subtle and easy to get wrong. So as a favorite example, the C++ standard template library had for many years the underlying data structure for its dictionary class was a red-black tree. And after it had been incorporated into the STL for about 15 years, someone actually looked at the code and realized that the deletion method was incorrect. It would delete the object, but there was no guarantee after the deletion that the tree would still be balanced, because they had made an off-by-one error, or they misordered one of the cases in the implementation of the red-black tree. And so Bob Sedgwick, the guy who did the quicksort analysis, who was also one of the original authors of the red-black tree data structure, first of all figured out a way of simplifying things a little bit and re-implemented the C++ standard template library to make sure this worked in 2003. Red-black trees have been around since 1985. So this is something that is surprisingly easy to get wrong, especially when you want to do deletions. So it's complicated. So I'm not going to do it. Right? I'm going to describe to you a randomized solution for keeping binary search trees balanced, which if you hold it up in a sort of engineering context and say, would I rather use a red-black tree or this randomized solution? In practice, if this is really the bottleneck, you really do want to use a red-black tree. It is somewhat faster. But if you want something that is reasonably good and easy to remember, and I can explain the entire algorithm to you in 15 minutes, with all details and all cases laid out to the extent that you can go home and implement it without getting it wrong, then the one I'm about to show you is better. Okay? And the simplicity of this algorithm comes from its use of randomness. So this is what's, this data structure is called the tree. This is by Cecilia Aragon and Raymond Seidel sometime in the late 80s, early 90s. And this is, if you're going to remember one balanced binary search tree, this is one of the two you should remember. Okay? So, what is a tree? So, a tree is a binary tree where every node has two values. Has a search key and a priority. Okay, and the idea behind trees is that simultaneously, exactly the same tree, you can look at as a binary search tree for the keys, and it's a heap, and in particular it's a min heap for the priorities, hence tree heap. Okay? So I have an example of one of these things on the next slide here. So this is a tree. The letters are the search keys in alphabetical, which you should imagine being in alphabetical order. The numbers are the priorities. Because English is weird, I'm going to use the phrase larger priority and smaller priority because in English, a higher priority means a smaller number. Priority 1 is higher than priority 2. It's bizarre, so I'm just going to say larger and smaller. So you'll notice that if I did an in-order traversal of this tree, I would start with nothing, and then A, and then G, H, I, L, M, O, R, T. That's in alphabetical order. So this is a binary search tree for the letters. But for the numbers, the only structure here is that the number at every node is smaller than the numbers in any of that node's descendants. So in particular, the smallest node is at the root. In any subtree, the smallest node is at the root. Okay? So this is a binary search tree for the letters, and it's a heap for the numbers. Okay? Now, I claim that, now having said this, having said I have these two design goals. If I just look at the blue stuff, it's a binary search tree. If I just look at the red stuff, it's a heap. That I have uniquely defined the data structure for any given set of keys and priorities. So if you just hand me a set of pairs of values where one is the key and one is the priority, I claim that this uniquely defines the structure. And so here's the proof. If there are no keys, then the empty structure is correctly both a binary search tree and a min heap for the empty set. Otherwise, the object with the smallest priority must be the root of the tree. By definition, because it's a heap with respect to the priorities. Because this is a binary search tree, any object that has a key larger than the key at the root must be in the right subtree. And anything with a key smaller than the key at the root must be in the left subtree. Yes? So none of these objects that have keys less than A go in the left subtree. All 0 of them correctly went over there, where by the induction hypothesis they formed the only possible tree for those 0 things. Similarly, the other 8 objects that had keys larger than the root went over to the right side, where by the induction hypothesis they formed the only possible tree for that set of 8 keys and 8 priorities. Now, it might be a little bit easier to see this if I, do this, one more time. In this right subtree, the object with the smallest priority is the one that goes at the root. Anything with a key smaller than the key at the root must go to the left. Anything with a key larger than the root must go to the right. And now, recursively, by the induction hypothesis, I have a unique tree structure on the left, and I have a unique tree structure on the right. Okay? So, the structure is unique. Provided, I'm going to make one simplifying assumption here, that any 2 nodes have distinct keys and any 2 nodes have distinct priorities. Question from over here. Okay. Yeah, if they're ties, then it's not uniquely defined. Because then there are 2 things with the smallest priority. You can make either one of them the root, and then the uniqueness properties go away. When I start talking about how trees are done just as a binary search tree data structure, there'll be a small probability of getting a collisions between the priorities, but that doesn't matter. Okay. So this is great. If I'm given keys and I'm given priorities, I can define this unique structure. It's not too hard to see that if I'm given priorities that are bad, in particular, if the order of the priorities is identical to the order of the keys, then the structure that I'm going to get is not going to be balanced. It's going to be as unbalanced as possible. But what I'm going to be using the priorities for is as a mechanism to balance the tree. Okay? In the original binary search tree problem, I'm only given the keys. It's up to the data structure itself to come up with appropriate priorities so that the resulting binary tree that you get by imposing the structure is balanced. Okay? So what we want to do is to say, given an arbitrary set of keys, I would like to find priorities so that the resulting tree is balanced. Now, I do want you to remember that the word arbitrary does not mean the same thing as the word random. When you start talking about inputs to your algorithm, you should not say, oh, given a random array. That's a very specific technical thing that means the objects are randomly distributed according to some probability distribution. Arbitrary means I know nothing about the set of keys except that they're a set of keys. Okay. Now, I can come up with a lot of complicated schemes to actually do this, but I'm going to choose perhaps just the laziest, simplest thing I can do, which is to say that priorities are random. This was Aragon and Seidel's insight. And in particular, for purposes of talking about the data structure, I'm going to assume a particular model of randomness. That means they're uniform real numbers in the unit interval from 0 to 1. Now, computers are not actually all that good about dealing with real numbers as first-class objects. We like things that can be represented with a finite number of bits. In practice, you can substitute a sufficiently large set of integers for the real numbers, and again, there'll be small collisions between the priorities, but they won't really matter. But for purposes of analysis, I want to imagine that whenever I get a new object, I assign it a priority. And I assign that priority uniformly at random between 0 and 1. And what this uniformity, because I'm working over real numbers, this implies that the priorities, no matter what finite set of keys I have, the probability of actually getting a collision between two priorities is 0. It's possible, but the probability is 0. For all practical purposes, it's impossible. It's not really impossible, but it's practically impossible. Okay? And that's really the only reason why I'm using real numbers instead of something discrete. Okay? So, why is this good? Well, actually, I basically now have told you almost the entire data structure, right? So you're given a set of keys, you just assign random numbers to them as priorities, and you build a tree. That's the data structure. Everyone think they can implement that? If you just given the stuff, you can build it from scratch, okay? Essentially, this previous slide, I showed you the algorithm. How do you find things in a tree? How do I say, is the letter R in this tree? You ignore the priorities and you pretend it's a binary search tree and you do what you were learned to do in 125. Or 225. Start at the root. If your target is bigger than what's at the root, you go right. If it's smaller, you go left, and either way you recurse. How do I insert something into a tree? Well, this is where I need to, for the moment, let me step back and imagine that the priority is really part of the input. And let's suppose, for the sake of argument, that I want to insert the letter S, and that the letter S has priority -1. I know I said reals between 0 and 1, but let's go with this as an example. Okay, so the way that you insert something into a binary tree is you apply the algorithm for searching for that object in the binary tree, and you notice where it fails. So if I'm looking for S, I'll follow this edge, then this edge, then I'll fall here, and I'll hit a null pointer, and I'll say, well, S isn't there. But then I take that null pointer, and I change it to point to this new object. Okay? Now this is a standard binary tree insertion, just like you learned in whatever data structures class. The problem now is that I've restored the binary search tree property for this new larger set of objects, but the heap property has been violated at exactly one edge. At this new edge that I just inserted, I have a larger priority above a smaller one. And so I need a way of fixing that. And the primitive data structure operation that I'm going to use to fix the priorities when they're broken is exactly the same operation that is used to balance AVL trees and red-black trees and so on, which is called a rotation. Okay? So let's say here I have some search key X and some search key Y, and these are subtrees A, B, and C. And of course, this is a child of some, some other node further up the tree. What a rotation does is essentially apply the associative law to the tree. I'm going to take the node X and I'm going to move it up. I'm going to take the node Y and I'll move it down. I'll arrange for, instead of Y being the parent of X, it'll be a child. And then I'll arrange the three subtrees, A, B, and C, in the only way that works to maintain the fact that this is a binary search tree. Okay. If you have left, right, and parent pointers, oh, what just happened? What just happened? Okay, I don't know what just happened. If you have left, right, and parent pointers, this is about a dozen lines of code with a couple of cases, depending on whether, if you're rotating to the right, whether Y is the left child or a right child. There are a couple of cases, but whether X is the right child or a left child. But this is really easy to write. It's just a matter of writing down the pointer changes in the right order. Okay. So interestingly now, if, say this is in a tree, and this node X has priority that is too small compared to its parent, then after I do the rotation, the priority order has been fixed locally. But it's possible that things are still screwed up with respect to the next node up. Moreover, if this edge from X to Y is the only place where the priority order is screwed up, then this edge leading up from X is still the only place in the tree where the priority orders are screwed up. So you notice everything in A has priority larger than X. Everything in B has priority larger than its ancestors, so larger than both X and Y. Everything in C has priority larger than Y. And so still, C is larger than Y, A is larger than X, and B is still larger than both X and Y. Okay. So if I want to fix the priorities here, what I need to do is a rotation. So let me see if I can do this rotation for you. Let me cut that edge for the moment. So this subtree is going to move down. This is going to move here. The subtree is now going to be the left child of the new node, and I still have one edge that's screwed up between S and its parent. So I can do one more rotation. So this subtree will actually move down to be child of S. This will go away, and this will move up to now be the right child of M. And still, I have one edge that's screwed up. And one more rotation will move S up all the way to the root, with M hanging down to its left. I won't try to do that last step on the fly. Okay. I'm supposed to read my mind. Okay, so we're still not quite done. There's still this edge that's screwed up, but everything else has been fixed. So the way that you insert into a tree is I'm going to assign X a random priority. I'm going to do the standard binary search tree insert of x. And then while the priority of x is smaller than the priority of the parent of x, I rotate x up. And I need another halting condition. If x ever becomes the root, then obviously it doesn't have a parent, in which case I just stop. Okay, this is the entire insertion algorithm. You already know how to do this. You chase the pointers down as if you're doing a search. The rotation is just 1,000 lines of code. You wrap it in a for loop. Done. How do you delete? Any guesses? Usually someone comes up with the right answer. Well, you have to be a little bit careful because the standard binary search tree delete, first of all, there isn't one. There are multiple ways to do it. Secondly, you want to make sure that when you delete, you make that the priorities among the nodes you leave behind still satisfy the heap property. Yeah.
So delete and then insert the nodes that are in the subtrees.
Okay, so the suggestion is, for example, if I want to delete S, I could just delete it, and then I've got 3 hanging nodes there, and I could reinsert them. That will work. The problem is that if I delete the root, I then am essentially building the entire data structure from scratch. Change the priority of the node you want to delete to what? Ah, good. So the suggestion is, let me change the priority of the nodes to something that would push it down to the leaf. So in particular, let me change the priority of this node to infinity. Now, if I'm in a tree where every priority is between 0 and 1, any node that has priority infinity, that's larger than every other node, so it cannot be an ancestor of any other node in the tree. It has to be a leaf. Okay? All right, so I'll set the priority to be infinity, and now I need to bubble it down to fix the priorities. But I have a choice. Do I bubble S down to the left, or do I bubble S down to the right? Sorry? Whichever has the smaller priority. I know when I delete S from that subtree, either R or T must be the new root, because this is the smallest priority in the left, and that's the smallest priority on the right. So within that subtree, I have to choose one of those two, and it's whichever one is smaller. So I'm going to choose the node that has the smaller priority and rotate it up, and that's going to bubble S down. And then if S is still has descendants, I pick whichever descendant has the smaller priority and bubble it up, and that pushes S down. And I keep doing that until S is a leaf, and then I knock it off. Okay? So the deletion algorithm is set the priority of X to infinity, and then while X is not a leaf, if the priority on the left of X is smaller than the priority on the right, then I'm going to rotate on the left side. Otherwise, I'm going to rotate on the right side. And then at the very end, X is a leaf, I just knock it off, delete it.
You do it the other way, like with the -1 there instead of infinity?
If you put a -1 there, it'll bubble up to the root.
Yeah. Does that work?
At which point, when you delete it, you've got these two treats which you somehow have to merge. right? What's interesting about these two algorithms is that they're exactly equivalent, except one of them is the other one running backwards in time. Right? So if you actually walk through the rotations that are done when you insert a new node and it bubbles up, and then you immediately delete that node and it bubbles down, it will perform exactly the same rotations, just in the opposite order. And this is a stronger statement than just it will restore the treat. If you insert and delete, you have to get the same treat that you started with that because there's only one treat for that set of keys and priorities. But the equivalence is stronger. It's really the same algorithm. It's just one is running forward in time and the other backward. Yes?
Would you violate the tree property if you just took the smaller child and made it the
So the question is, why not just move the smaller child, swap those two nodes, for example? And the reason I don't want to swap those two nodes is that will violate the binary search tree property, the keys. So for example, if I wanted to delete M, and at this point H has the smaller priority, so I'd want to send M down to the left. If I just swapped M and H, then this would no longer be a search tree because I is over here on the left, even though I is after H in sorted order.
I mean, just delete M in general.
I'm sorry?
Just delete M in general.
I don't know what delete M in general means.
Remove all pointers to it, and then put H to the left.
If I delete M, I'm left with these two subtrees that I have to reconnect somehow. So I want to be, in general, there's some ideas about possibly, can I move the nodes around in some other way than doing rotations? And maybe. The nice thing about rotations is that they're guaranteed to transform a binary search tree into a binary search tree. I don't have to do any special case proving that the operations I'm doing work because I already know that rotations work. Right? That may not be the only way of manipulating these things, but it's there and it's standard, and I have no more cases to worry about. Okay. So I've now described the entire algorithm to you.
This is looks that easier compared with AVL tree.
Yes.
This looks kind of the same at the same level at the same time.
Except that AVL trees have cases.
Oh, yeah.
Right? This has two cases. Is this if true or false? Do I rotate on the left or do I rotate on the right? Those are the only cases, and you just comparison, and you can remember what the two cases are by saying, oh, I have to have a heap. So the smaller thing has to go up. Whereas with AVL trees, you've got these bits that or counters that are measuring the difference in height, and it's maybe +1 or -1 or 0 or +2, and if it's +2 on the left and it's +1 on the right, then you do it this way, and if it's, I can never keep these, I've never been able to keep these in my head. Okay. It's true that it's only 50 lines of code, but my goal here is to have something that fits in your head, not on the page. Okay. Anyone have any doubts that they can implement this if they had to? Good. When you interview at Facebook and they ask you to how would you implement a balanced binary search tree? You can say, how much detail do you want? Okay, so we've built the structure, we've done insertions, we've done deletions, we've done searches because searches are just standard binary search tree stuff. The cost of doing a search is the depth of the object that you're looking for, or its predecessor or successor, depending on whether you're doing a successful search for something that's in the tree or an unsuccessful search that something is not. When you do an insertion, the depth here at this stage, when you insert that node, that's really what's dominating the running time. You walk down the search path and possibly you rotate back up. So the length of the search path is the thing that is going to matter for insertion. And similarly for deletion, because deletion is just insertion and backwards in time. Okay? So this means is, if I want to do time analysis for each of these operations, is the depth of some node in the tree. Either the one that I'm searching for or inserting or deleting, or the one that's just larger or just smaller than the one I'm inserting, deleting, or searching. Okay? So now my claim is, to finish the analysis, is that for every key x, the expected depth of x is log n. Now remember, this is in a tree where I'm generating the priorities randomly. The randomness hasn't come in anywhere yet. It's not really an important feature of the algorithm. The correctness of the insertion and deletion routines don't depend in any way on randomness. It's just an initial random assignment, right? This is where we're actually going to be using the fact that if all priorities are random, then the expected value of the depth is going to be log n. Okay? So to prove this, I'm going to use the definition of depth. What's the definition of depth? What's the depth of a node in a tree? What does that actually mean?
Distance to the root.
Distance to the root. Okay? Distance meaning
Number of nodes.
number of, actually formally it's the number of edges. I'm going to define the depth of the root itself to be 0. Another way of saying this is that the depth is equal to the number of proper ancestors. Right? These are, if I go to my parent, and then my parent's parent, and my grandparent's parent, and so on, all the way up to the root. So if I'm the root already, I don't have any proper ancestors. Okay. So I'm going to define I can talk about the expected depth by asking about the expected number of proper ancestors. And the way that I'm going to do that is I'm going to say, if you're my proper ancestor, you're going to pay me $1. And if you're my proper ancestor, you're going to pay me $1. And if you're my proper ancestor, you're going to pay me $1. What's the expected number of dollars that I get? Well, it's the probability that you give me $1 plus the probability that you give me $1 plus the probability that you give me $1. So this is just the sum over all nodes V of the event V is a proper ancestor. So if I want to look at expected values, I do exactly the same trick that I did with nuts and bolts before. It's to say the expected value of this sum is the same by linearity of expectation as the sum of the expected value of these 0 and 1 variables. But the expected value of a 0 and 1 variable is just the probability of that variable being equal to 1. So in order to analyze the depth of a node, I just need to figure out what's the probability that one node in the tree is a proper ancestor of another. Okay? So I'm going to write, to give myself some notation here, I'm going to write this event I above k. Right? This is completely non-standard notation, but I'm trying to make it mnemonic, and so it's easy to remember. This is 1 if the node with the ith smallest key is a proper ancestor of the node with the kth smallest key. Okay, I'm gonna really hate writing this a lot, so I'm gonna call this node I, and I'm gonna call this node K. I'm going to imagine that the keys, for the sake of argument, since it's really only the order of the keys that matters, I'm going to imagine that the keys are themselves the integers from 1 to n. And when I say node 5, I mean the node with key 5. Okay? So let's see if we can figure out what's the probability. Now notice, this is again entirely based on the random priorities. So the way that I want to think about this is by going back and looking at the proof that the tree structure is unique once I've decided what the priorities and the keys are. So the keys have been given to me, and only their order matters. So here they're letters instead of numbers. And let's imagine that these numbers I put in were generated randomly. The way the tree is defined is I say, I'm going to pick out the key with the smallest priority. Okay, the priorities are random. So every key is equally likely to be the one with the smallest priority. So let me say what I just said again. Pick out a random key. Put it at the root. Anything whose key is smaller, I'll shuffle over to the left. Anything whose key is larger, I'll shuffle over to the right. Then I'll recursively build a tree on the left, and I'll recursively build a tree on the right. This sounds familiar, I hope. What did I just describe? Quicksort. Choose a pivot value. Anything that's smaller goes to the left. Anything that's bigger goes to the right. Recursively do whatever you're doing on the left. Recursively do whatever you're doing on the right. This tree is the recursion tree for quicksort, provided the pivots are chosen in the order specified by these priorities. So at the very beginning, I'll choose, remember, these priorities I've generated with random values. I'll choose randomly the object that has the smallest priority, and I'll split into 2 smaller problems. And then I'll recursively, inside each subproblem, I'll choose the key with the smallest priority and partition and recurse again, right? So, this is actually relatively important. Tree is a recursion tree for quicksort. Now, under what circumstances is one node a proper ancestor of another? Well, let's take the look at the node that was higher up, the one I'm claiming is the proper ancestor. What this is saying is that the other one somehow is a descendant. But which nodes can be descendants of L? These are the nodes that were partitioned when I randomly chose L as a pivot. Right? I didn't include A because it had already been chosen somewhere else. So L's proper descendants are precisely the subset of nodes that when I choose L as a pivot, L partitions. Now, when I run quicksort, the way that I partition is I compare L to everything in the block of objects that it partitions. That's how I partition. So L is a proper ancestor of R because in quicksort I compared L to R. The proper ancestor relationship in the tree is the comparison relationship in quicksort. Sort of. Because there are two things that might happen if I compare L and R. One of them is that L is the pivot, in which case R is going to be lower down. The other one is that R is the pivot and L is further down. So there's a 2-to-1 relationship, if you like. Okay. So this, probability that I is above K, this is equal to the probability that quicksort, remember randomized. Let me put a little squiggle here. It's sort of equivalent. The probability that randomized quicksort compares I and K. Right, if I want to remove the equivalence, I would say when I is pivot. Okay. And essentially, you already know how to do this. Okay. So I'm going to write down again my block of nodes by random order. But in order by search keys. 1, 2, all the way up to n. And then I'm just going to pick out 2 nodes, I and K, and ask, under what circumstances is I going to be an ancestor of K? Well, my claim is that what I need to do is look at the subset of keys whose values are between I and K, inclusive of the 2 endpoints, and ask which key in that range has the smallest priority. If the answer is I, then I will be an ancestor of K. If the answer is anything else, then I will not be an ancestor of K. If the answer is K, then K will be a proper ancestor of I. So let me define, just to give some notation here, let me define this set xik. This is the set of all integers between I and K, or K plus 1 up through I, depending on whether which order. If I is smaller than K, I want this one. If I is bigger than K, I want that one. Right? And so my claim is I is above K in the tree if and only if the smallest priority priority in xik is node I. Okay. So, let me see if we can do the proof. Let's start by going this way. Let's assume that I is an ancestor of K. So here's node I, and somewhere down in its search tree, there's node K. Well, there's this wonderful property of binary search trees that if I have an ancestor if I is an ancestor of K, then every node that's between I and K in terms of rank has to be somewhere in this subtree. Right, so this is xik. All those nodes, they can't be further up, because if anything that's above here is either going to be smaller than I, or smaller than the smallest node in the subtree, or bigger than the biggest node in the subtree, therefore bigger than K. So anything above or outside or over, left or right is either going to be smaller than I or bigger than K. So all of xik is in here, and I is, by definition, the node with smallest priority in this whole subtree. And so it must be the node with smallest priority in xik as well. Good. Did I go too fast? Did you get it? Suppose we go this way and say, well, suppose for the sake of contradiction that the smallest priority in xik is actually node j. Okay. Then I want to claim that I want to imply, from this, I'm going to infer from this, excuse me, that I is not an ancestor of k. And so what I'm actually going to end up, this will imply essentially by the let's see if I can say this the right way. Yeah, I think I have to go back to the view of trees as the recursion tree for quicksort. At some point during the randomized quicksort, I'm going to be faced with some block of nodes that includes I, j, and k. And the first time I choose a pivot that's in this range from I to j is node j, because that's the one that has the smallest priority. Yes?
I'm a little confused. What's the triangle on the
This triangle on the left is the subtree in the tree that is rooted at node I. K is I'm saying, suppose I is an ancestor of K. Then, by definition of ancestor, K must be in the subtree rooted at I.
So we're ignoring the whole quicksort thing now?
On this side of the proof, yes. I'm just using the fact that it's a binary search tree. On this side of the proof, I really want to think in terms of quicksort. Okay. But if j is the smallest thing, the smallest priority in this range, that means I'm going to choose j as a pivot before I choose anything else in that range, which means I'm going to send I off to the left and k off to the right, and so they're not going to be ancestors of each other. Okay. All right. So if we accept that that claim is true, and if that went a little bit too fast, I encourage you to look at the notes. Sorry, let me say this as a probability. The probability that I is above k is the probability that I has the smallest priority in this set xik. What is that probability?
1 over a minus I.
So it's 1 over the size of xik, because every item in that set is equally likely to be the one that has smallest priority, which is 1 over the absolute value of k minus I plus 1, if you're watching carefully. Okay? So now, if I ask, what's the expected depth of node I? This is just the sum over all nodes k of the probability that I is above k. Okay. Which is the sum over all I less than k of 1 over k minus I plus 1, plus the sum over all k, this should be k less than I and k bigger than I. Is less than I, but sorry. I minus k, 1 over minus I plus 1. This is less than 2 times the nth harmonic number. Each of these sums has at most n terms, and they start out 1/2, 1/3, 1/4, 1/5, 1/6, and so on. Similarly, over here, walking backwards, 1/2, 1/3, 1/4, 1/5, and so on. So if I just assume, I know that the total number of items in these two sums is n minus 1. If I just say, okay, conservatively, let's continue this sum out to n terms, and let's continue that sum out to n terms, then each of those sums is going to be exactly the nth harmonic number. Okay. In reality, it's going to be something like hk plus h of n minus k plus 1 minus 1 or something. But I really want to be pedantic. But this is 2 times natural log n.
It's actually the probability of
K greater than I.
I'm sorry?
it's sigma k go to the I.
This is
It's usually
k less than I, overall k that are less than I.
The previous line.
The previous line.
K greater than I. No.
So I'm trying to find the depth of I.
Yeah.
So for all other nodes k, I want to know what's the, oh, you're right. Okay, fine. Sorry. Got this backwards. K above I. It turns out not to matter.
Yeah.
Right? The probability k is above I and the probability that I is above k is identical. But if we're being careful, which I wasn't, and I apologize, I want to write the thing whose depth I care about on the right side of the arrow, and the other node on the left. So as you might have guessed from the symmetry here, the other thing that you can ask is what's the expected size of the subtree rooted at I? This is the number of proper descendants. And you end up with exactly the same calculation, except that you just swap these 2 letters and everything else is identical. So for any particular node in the tree, even though the tree itself has n items, if you pick a node and say, node 7, out of all trees built out of these n nodes, what's the expected number of descendants of node 7? 2 log n. And so that's it. That's trees. The entire algorithm, the entire data structure, insertion and deletion routines, and the analysis. Yes? N is just the total number of nodes in the tree. So there are a total of n minus 1 nodes in these 2 sums. All the nodes that aren't node I. There are n nodes altogether, and one of them is I, and I'm interested in how many of the other ones are proper ancestors. So I said, okay, this is some harmonic number, 1/2 plus 1/3 up through actually 1 over I, 1 over I. And this is some other harmonic number. And since I'm really only care about this up to big O anyway, I'm going to conservatively say, let's just run each of these sums instead of stopping early. Let's just imagine that each of these sums runs up to n terms. And so we get a conservative upper bound here. In fact, what the tree looks like is sort of the expected shape of the tree. It's like this, where on the edges, the largest and smallest nodes in the tree have depth. One of those 2 sums just vanishes. In the middle, it's about twice as deep. So it's not going to be like the shape. The expected shape isn't like a perfectly balanced tree where all the leaves are roughly the same level. Smallest and the smaller and larger extremes are going to be about log base e of n, which is actually less than log base 2 of n. And the stuff in the middle is going to be a little bit deeper. So this red triangle sort of intuitively shows you what a perfectly balanced tree would look like. It's shallower altogether, but it's a little bit deeper than a tree. Any questions about this? Yeah.
So I still don't really understand why there's
I'm
not equal to I, but like they could be either in like the subtrees below I or
no. So okay. So the reason why I have two summations here is that I don't like summations with absolute values in them. So there are two cases. One is where k minus I is positive, and so I don't need the absolute value. And the other case is when k minus I is negative, and so the absolute value swaps them. Which is why I have k minus I on one side and I minus k on the other. Okay. Now, I do want to point out that there's a sense in which this result is a little bit weak. Because what it says is, here's a set of n items that I'm going to lay out on the table. You point to your favorite item, and then I guarantee that when I build a random tree, that item will, in expectation, have depth of most 2 log n. But at some level, you'd like to be able to make the following stronger statement, which is, I'm going to build a tree. And then after I'm done building the tree, you're going to point at an item and say, what's its depth? Which means, of course, you're going to point at the deepest thing in the tree. Right? So what we've shown is, for all x, the depth of x is in expectation log n. But what I want to know is what's the maximum depth in the tree. I build the tree and I say, okay, now that I built it, what's the deepest thing? This is a stronger guarantee, right? And it turns out that this is also log n. Right? This is not, by the way, immediately implied by the first thing. Because it's possible that in a tree, there's always one item that's really, really deep. It's just very rarely, you could imagine a distribution over binary trees, for example, that you always get a binary tree that looks perfectly balanced except for one long hair hanging down. And that hair is equally likely to be anywhere, which means it's very unlikely to be any particular node. Right? But after I built the tree, maybe there's always some really awful thing in it. And so I want to quickly convince you that that can't happen. And the argument for why that can't happen is essentially the back of the envelope analysis of randomized quicksort. So I want to ask, what's the probability that the maximum depth is bigger than, say, 4 natural log n? Okay? So I'm going to look at it the following way. Again, I'm going to imagine that I'm doing quicksort, but I'm now going to look at the tree level by level. Okay? And I'm going to say that a level is bad if I look at some subproblem somewhere at the level, the biggest subproblem is split badly. Okay? So let me define sorry, as you might guess, I'm improvising here. So remember what the definition of a bad pivot was in randomized quicksort. A bad pivot was one that was not in the middle half of the block that we're trying to partition. Okay. So if we imagine taking the tree and building it by doing randomized quicksort. So I choose a random pivot, and then I partition the data into 2 smaller blocks. And then each of those, I'm going to choose a random pivot. And I'm only really interested in the larger of the largest subproblem on this level. Okay. This is a reasonably good pivot because the two problems are roughly the same size. This is a bad pivot because one of the subproblems is really awful. Okay. Okay. So the probability that a level is bad is a half. Okay, I'm just going to define it that way. Now, the maximum number of good levels I can have is log base 4/3 of n. Because every time I have a good level, the largest subproblem on that level decreases in size by a factor of 3/4, right? It gets, reduces by 75%. Which means after I've reduced my original problem of size n, I've multiplied by 3/4 this many times, I'm going to be left with only a level where the largest subproblem has size 1. And the tree can't get any deeper than that. Okay? So what I'm really now interested in is what's the probability that the number of bad levels is, say, bigger than 3 log n. Okay? And morally, this is equivalent to saying, if I flip a coin, say, 4 log n times, what's the probability that I get 3 log n tails? Okay? The probability that a given level is bad is a half. So in terms of the analysis, I could just say, at every level I flip a coin. If it comes up heads, the level is good. If it comes up tails, the level is bad. I know after I flip heads this many times, God is going to take the coin away. And so the question I'm asking is, can I flip tails a lot before God takes the coin away? And another way of saying that is if I flip the coin a lot, what's the chance of getting really an enormously larger number of tails than what I would expect? Right? If I flip a coin 4 log n times, how many heads do I expect to get? What's the expected number of heads? 2 log n by linearity of expectation. Okay? Generally, if I flip a coin k times, I expect k over 2 heads. And so what this is asking, and k over 2 tails, what this question is asking now is what's the probability that the number of tails I get is way bigger than what I expect it to be? Right? This is what's called the tail inequality. What I can ask, for example, is what's the probability that a given random variable x, this is the number of tails that I get when I flip the coin too many times, is bigger than some constant times the expected value of x. Okay? And on Thursday, I will tell you how to think about inequalities like this. For now, I will just reveal that this probability is exponentially small in the number of coin flips, right? So this is going to turn out to be something like 2 to the minus 3 log n, which is about n to the minus 3. Tiny. Okay? There's some small polynomial probability, inverse polynomial probability, that your tree is not going to have all of its nodes shallow. And keep in mind that when n is 1,000,000, this probability of failure is 10 to the minus 18. Right? If n is a billion, this failure probability is 10 to the minus 36. It's not 0, but it's sufficiently small that even if you're Google, you don't care. Right? And the very, very small chance that you actually end up with a treat that's badly balanced, you just say, oh well, sorry, and you rebuild it with new random priorities. But that's so rare that it has no effect whatsoever on the performance in practice. So with this, I think I'll let you go. I'm happy to answer any questions though. Thank you.
Chef, any comment?
Yes.